Ladies and gentlemen, good afternoon and welcome to the reveal of the very first images of ESA's Euclid mission. My name is Cara Monter and I will be guiding you through our program for the next 40 minutes where we take a look at these wondrous images of Euclid, together with scientists and experts working on Euclid. Today, I am here in the Mission Control Room in ESA's Operations Center in Darmstadt, Germany, where engineers are flying and caring for Euclid 24/7. And I will soon be joined by the head of ESA's science program, Carol Mundell. To be honest, it feels like only yesterday that Euclid left the Thales Alenia clean room in Cannes for its journey to its launch pad in Florida, and then from there, of course, into space. And we're going to have a look at that now.
3, 2, 1, ignition, liftoff. Spacewalk propulsion is nominal. Vehicle is pitching downrange.
Hey, they're all positions loaded. We have a signal from Euclid in space.
Yes.
Still get goosebumps watching that. I'm now joined by Carol Mundell, head of ESA's science program. Hi, Carol. What's been happening since Euclid launched into space 4 months ago?
Well, Chiara, welcome, and what a great day. It's a great pleasure to be here and welcome all of our views on behalf of the European Space Agency. So I was there in Florida for the launch. It seems, as you say, only yesterday, but since then our teams have been working tirelessly to do the engineering verification of the mission. So obviously in our labs on the ground, we do everything we can to make sure that the mission and the spacecraft and the instruments are absolutely perfect. But it's not until you fly into the depths of space and you try out your instrument for real as to whether you figure out whether everything's okay. And so we've had a few engineering challenges through the summer. The teams have been working day and night to actually beat those challenges, and actually today is an iconic day because I'm absolutely delighted to say that this is the point where we say that we have reached all of our engineering milestones for the mission, and we're now able to move into the science phase, and so it's a really special day today.
It's super exciting. I'm really happy to be here. Can you explain to us, though, why these images are unique, the ones that we're going to see?
Yeah, so what you're going to see today is really a test or a testament to the perfection of the instruments, the mission and the optics, and how they've all been built and delivered up into space. And so what we're going to see are exquisite images over vast areas of the sky, taken actually very quickly to great depths with razor-sharp precision. And it's those ingredients pulled together that is going to make Euclid the iconic cosmology mission of the day.
Fantastic. I think I speak for all of us when I say that I'm really excited to reveal the images. But first, let's remind ourselves why Euclid is such an important mission.
In 1915, Albert Einstein astonished the world with his general theory of relativity. It described the behaviour of the entire universe based on the matter and energy contained within it. The theory sparked the modern discipline of cosmology and the hope that we would finally understand how the universe came to be. But in recent times, the effort to define what the universe is made of has given us a very big surprise. Visible stars and galaxies make up less than 5% of the universe's total matter and energy. Beneath this visible layer is a mysterious celestial realm, consisting of shadowy particles and unknown energy fields. For decades, astronomers have puzzled at their nature, calling these elusive substances dark matter and dark energy. ESA's Euclid mission will go in search of the answer to the fundamental question: what is the universe made of? A European-designed mission, Euclid is built and operated by ESA, with contributions from the International Euclid Consortium and NASA. ESA selected Thales Alenia Space to lead on building Euclid, with Airbus Defence and Space providing the telescope and payload module. The telescope and scientific instruments form the heart of the mission. Together, They will observe billions of galaxies over more than 1/3 of the sky. Producing record quantities of data, Euclid will enable scientists to draw a precise map of the universe across space and time. This will allow researchers to investigate the effects of dark matter and dark energy on the apparent shape of galaxies and on their motion and distribution over immense distances. In turn, this will help reveal the true nature of dark matter and dark energy. The spacecraft and data communications will be controlled from ESA's European Space Operations Centre in Darmstadt. To cope with the vast amounts of data Euclid will acquire, ESA's EdgeTrack network of deep space antennas has been upgraded. These data will be analysed by the Euclid Consortium, a group of more than 2,000 scientists from more than 300 institutes across Europe, the US, Canada, and Japan. Understanding the elusive nature of the universe has drawn astronomers throughout history. It remains one of the most challenging investigations in modern science, but Euclid is up to the task. The Euclid mission is a quest into the unknown, a mission to shine a light on the dark side of the universe.
Carol, Euclid is evidently a very ambitious mission. Could you tell us more about why it is so special and how it fits into ESA's wider space science program?
Yeah, indeed. I mean, Euclid alone is actually breaking many firsts, both in terms of the science that it will address, the technology that we've developed in order to address those fundamental questions, as you saw in the clip. And it's going to survey 36% of the sky, which is the entire extragalactic sky, back to 10 billion years of cosmic history. It's got incredible precision for measuring the shapes of galaxies, so we understand the optics very well. We'll also be measuring where they are in 3D. So we'll actually make the largest 3D catalogue of the universe, which is very much similar to what we did with Gaia for the Milky Way. So the ESA Gaia mission actually measured the properties of billions of stars in our own Milky Way galaxy. Now we'll do billions of galaxies in our universe. And of course, Euclid really sits at the heart of a suite of missions that we've flown from our ESA portfolio with our collaborators and our member states over the last many years. So it's building on a legacy from the Planck satellite, which was a cosmology satellite that ESA led, that really looked at the beginning of the universe and the seeds of the structure that we think now have evolved into the galaxies and the structures that we see today. And it was really Planck that showed us that 95% of the universe was unknown to us, and that's what Euclid is going to unveil. So it sits in a wider suite of astrophysics missions, and then of course we have missions that study everything from above the Earth's atmosphere out through the solar system and out to literally the edge of the nature of space-time.
Fantastic. And I mean, Euclid is an ESA mission, but it's a huge collaborative effort as well. How do we make sure that all of these parties come together to create a successful mission?
Yeah, I mean, it's an incredibly, powerful and inspiring collaboration. And so people have spent many, many years, I mean, some people have spent 10 or 12 years of their life on this. Our scientists formulate those big questions that we want to answer. We have something like 2,500 scientists who have or who will work on this mission through their careers. And we brought together 2,000 industry partners, so both in industry and both in our labs within ESA, to actually devise, invent and realize that technology. And then we all pass on the baton to one another. So I think, when we launched, there were teams who, of course, had finished their work at the time of launch. There were teams that helped us into the beginning of the engineering commissioning. Now our engineering teams will now pass on the baton to our science collaboration. And the Euclid Consortium, of course, will then do the cosmology over the next 6 years. And then, of course, we have our international partners. So this was a really strong collaboration with NASA, who provided one of the instruments on board. And so putting all of that together, it's truly an international collaboration, on behalf of humanity to study the nature of the universe.
It's really incredible to hear how many people have come together for this. I'd also like to thank the Euclid Consortium for providing this video footage that we've just been seeing. And thank you, Carol. Now, we are getting very close to showing you Euclid's first 5 images. They demonstrate Euclid's potential to change the way we see the universe. But before we dive into that, we have a short message from our Director General, Josef Aschbacher.
Good afternoon, dear friends and colleagues in ESOC. I'm joining you from the European Space Summit in Sevilla, from an event full of exciting energy as we plan Europe's future in space. In a few minutes, we will release the first images of Euclid, What a special moment. A mission that will reveal the invisible 95% of the universe, which is truly incredible, and a milestone for ESA's world-class space science program. Extraordinary, ambitious missions like Euclid encounter challenges along the way. And all these challenges were successfully overcome thanks to the many dedicated people. Seeing Euclid now ready for science is a proud moment for all of us. A milestone for European science and exploration. Seeing Euclid now ready for science is a proud moment for all of us, a milestone for European science and exploration, and our leadership in science and technology. With over 3,600 people who have contributed and a consortium of over 2,000 scientists, Euclid is also a strong statement for the power of international cooperation. It shows the strength of our partnerships with the world's most capable experts, agencies, and industrial partners. I would like to thank and congratulate our member states, the Euclid Scientific Consortium, NASA, Thales Alenia Space, and Airbus Defence and Space, as well as the teams at ESA for this outstanding achievement. I'm looking forward to the many exciting insights that Euclid will bring us, especially to help us understand what dark matter and dark energy really are. Thank you.
The time has come for images, ladies and gentlemen. These images were all taken as part of a special program to examine a set of celestial targets chosen for both their public appeal and scientific value. In total, the program took less than 1 day of observation time out of a 6-year mission. With these images, we will begin looking far into the distant universe, with each image gradually coming closer to Earth. Carol Mundell, head of ESA's science program, is still with me to reveal the very first image. But before you do that, could you give us a sense of the scale of these images that we're going to see?
Yeah, absolutely. So in a single shot, we have a number of CCDs. So this is what Euclid sees when it first looks on the sky. And to give you a sense of how vast this is, it's actually bigger than about 2.5 times the surface area of the moon when we put that onto the sky. And I'm told that there are about 600 million pixels in there. So this is a mega camera by all accounts. And it's got exquisite sensitivity and very, very, very high precision. So you combine all of those together, and that actually explains why we could make these incredible observations that we're about to see in such a short space of time. When we do the cosmology survey, we will do 30,000 of these pointings, and so that's going to be a vast data rate coming down to our data centers.
Wow. And I think we're ready to reveal the first image.
We are.
Right?
So this is a really exciting moment for me. I'm going to take a breath because this is an iconic moment. So, you know, thank you to all of our viewers and all of our stakeholders and everybody who's made this possible, and particularly our teams who've been working on these images tirelessly. So it's a great delight. And without further ado, I will now reveal the first image in our sequence. And here is the first sight of our Euclid image.
Thank you for introducing this first image, Carol. Maybe you can tell us a little bit more about what we can see here.
Yeah, so dazzling, I think, is the first word to describe here. So what you can see here is one of the biggest gravitationally pulled together structures that we have in the local universe. This is a galaxy cluster called Perseus, and we'll hear a little bit more about that shortly. And we expect to find many of these in the Euclid universe. But each of the dots on this image, most of them are galaxies in the distant universe. So we think there's something like 100,000 galaxies in this slice of the sky, going back into cosmic time about 10 billion years. And then we've got nearby galaxies and all of those distant ones. And so there's a huge amount of data alone in this image to mine. In fact, I was already zooming in on this when I had a sneak preview. So there's
we
a
can
lot.
even zoom in a little bit.
We can actually. I think there's probably a zoom we have now. And you can start to see the distant points, but actually even nearby, we've got distorted galaxies. We have pairs. We have lovely spiral galaxies, a bit like the Milky Way. So we've got all sorts of things in here. I know our scientists will probably be going to ESA Sky to dig into this. And then, of course, you can see these distant objects. These bright things here that actually have the spikes, these so-called diffraction spikes, these are stars in our own galaxy. And so, obviously, we'll also be able to do some galactic science for free along the way. But, yeah, there's just so much rich science and physics to be extracted from these images. And, of course, the colours themselves tell us something about the physics encoded in the light, too. So we've got lots of codes to decode as we work through this. But what we also know is that the dark matter and dark energy and the physics that govern those are also encoded in the shapes and the structures and the patterns that we will see with these Euclid images as we build up the survey.
It's so incredible to hear how much can come out of these images. I'm very happy to also be joined by Jean-Charles Couillondre, an expert in wide-field ultra-deep imaging. Jean-Charles, can you explain a bit about what these galaxies that we see here will tell us?
So this large image, which captures the whole field of view of Euclid, actually is pretty obvious. You have some large objects which are actually sitting on the tip of your nose because they're only 200 million light years away. And like Carol just said, like if you project that same structure beyond, you will see all these little dots. So it's kind of the universe repeating itself in this structure on and on. So what we know with this structure, you almost can see it on the screen, is that we talked about filaments and dark matter and dark energy. And so we know there's a cosmic web. That's the way the universe is structured. And clusters usually condense at the crossroad of filaments of dark matter. And so this is a great example because we know from looking at all these galaxies that you have a filament that go left to right. You almost see it, right? And one which is top down, which you almost get a sense because of this overdensity of galaxies. And so that's why this Perseus cluster is a good sample for now to study, well, the astrophysics, how objects do behave in this sort of environment.
Fantastic. And I think we even have a closer-up view of the Perseus cluster.
Yeah, so in this one, just like Carol was mentioning, we see like a diversity of types of galaxies. You have spirals, you have ellipticals, and then we have also dwarfs, tons of dwarfs, because the smaller you get into the zoo of galaxies in clusters, the more you find them. And so this field already has revealed tons of these dwarf galaxies. Very exciting.
Fantastic. And Carol, we've imaged the Perseus galaxy cluster before with other telescopes. What makes Euclid's view so special?
I think there are two things that are very special about Euclid. The fact that we can do such a broad area immediately. So as Jean-Charles said, you see immediately the cosmic structures, which, you know, scientists in the past have painstakingly tried to take little pieces of the data. You know, you find a galaxy, you measure its position, and then you slowly build up this map. So they were really the forerunners for this. We knew that there was a hint of these filamentary structures, and that was really what motivated us to actually to build this mission. And immediately it pops out, as you know, just one image, there you go, there's the filament. So think of the potential of that, but also the fact that it is so sensitive, as Jean-Charles says, it's sensitive enough to pick up the smallest galaxies, which are faint, but it also has exquisite precision in its optics. So these faint small galaxies, if we look from the ground, they would be merged in. We wouldn't be able to distinguish them in detail. And if we look at them with current space missions, for example, Hubble, which has been great, and Webb as well, which is doing really important work, we would only be doing a little patch of the sky. So it's combining that wide area, the depth and the precision. You then get these crystal clear, stunning images going back in cosmic time.
Fantastic. Thank you so much, Carol and Jean-Charles, for joining me. I mean, wow, this image has really demonstrated how much of the cosmos Euclid will reveal. And this image alone contains 100,000 galaxies. Over the next 6 years, Euclid will map a region 30,000 times bigger than this one, meaning that it will measure the shapes and positions of literally billions of galaxies. Now, our second image brings us somewhat closer to home, 10 times closer to be exact. And it's a beautiful example of how Euclid will reveal previously hidden individual cosmic objects. Let's have a look. this galaxy is nicknamed the Hidden Galaxy because it lies behind lots of dust, gas, and stars. And I'm happy to be joined by two ESA scientists. We have Guadalupe Cañas-Herrera and René Laurès. René, you are the project scientist for Euclid. Could you tell us how Euclid allows us to see this hidden galaxy?
Right, this galaxy is in the plane of our own Milky Way. And because of that, we look through many stars, past many stars, and also gas and dust in our own plane. Euclid looks in the infrared and in the red. So it's false color, what you see here. What is blue in this image is really red in real life. And what is red here is infrared, so it's invisible in real life. So what we see is basically the infrared and blue and red light from this galaxy. Now, why in the red and the infrared? Imagine the sun coming up, it's red. And that's the reason why, that's because blue light is scattered away or absorbed by the dust and gas in our own atmosphere. Now, the same happens to this galaxy.
And I think we can see what infrared achieves here on the screen.
Yes.
Right?
You see a little galaxy in the middle. Mm-hmm. So we don't look only through our own galaxy, but even through this big galaxy to see the background galaxies. So this is amazing what infrared is doing.
Incredible.
And you also see all the details here, the little stars around, and this is in the spiral arms of this big galaxy.
Fantastic. Guadalupe, as a cosmologist, you must have seen images of many galaxies. How does this one compare? I think we can maybe go back to the big image and take a look.
Yeah. Right, the galaxies that I'm used to seeing, actually, they're like the small galaxies that we were seeing resolved in the arm of this amazing spiral galaxy, but it's just breathtaking. If I envision myself, if I have to imagine for a moment a spiral galaxy, it will be really close to this spiral galaxy. And it's thanks to this kind of galaxies that we can actually study an indirect detection of dark matter, because we study the rotation of galaxies like this one to actually infer how much dark matter we have in our universe.
So cool. And I mean, this galaxy does look very similar to the Milky Way galaxy, our own galaxy. How can studying galaxies like this one help us study our own home in space?
Right, so as you said, we are in our Milky Way. We know that it is a spiral galaxy, but as we are inside the Milky Way, we cannot actually see the whole galaxy. This is why we rely on spiral galaxies like this one to infer features and the nature of how these galaxies behave. So not only how they have formed, but maybe even their eventual fate, for instance.
Fantastic. And we also hear that Euclid, as you mentioned already, will tell us a lot about dark energy. René, what does this beautiful spiral galaxy have to do with dark energy?
Right, that's a good question. Euclid will observe more than billions of galaxies in order to derive the structure of our universe. Now, if you observe 1 billion galaxies, you have to start with one. And this is the one. So many of these billion galaxies will be like this galaxy, and we will measure the shape as well as the distance to all these galaxies in order to derive our science from it. So that is the dark energy and the dark matter distribution.
Fantastic. Thank you so much, René and Guadalupe, for joining me.
Thank you.
Isn't it amazing to believe that this image just took Euclid 1 hour to create? The fact that Euclid can take these large images so quickly is one of the things that makes it unique. When we look at this image, it is worth remembering that over its lifetime, Euclid will image billions of galaxies to reveal the hidden influence of dark matter and dark energy. But now, many galaxies don't look like these quintessential spirals that we have just seen, but are smaller and lumpier. And these are called irregular galaxies. Now, our next image is an example of a small irregular galaxy. Let's have a look. So this galaxy is relatively nearby, so a neighbor, so to say. But many distant galaxies show us the early universe are actually, in fact, irregular galaxies. So now I am here with Francis Bernadeau and joined again by Jean-Charles Coulondre to find out more about this image. So Francis, Can you tell us what's so special about this image of the irregular galaxy?
Yeah, what's so special is, yeah, thank you. I mean, what we should keep in mind that Euclid is has unique capabilities. This is the first telescope which can capture in one single exposure the entire galaxy, the surroundings, with this exquisite resolution. So you have very sharp images all over the image. So that's unique in the sense that even though you may have satellite out there, I'm thinking of the James Webb Space Telescope that have also very good resolution, but the field of view is much smaller. That is, the areas that can be captured in one single exposure is much smaller. The Euclid field of view is about 100 times bigger than the one of the James Webb Space Telescope, and that's unique for Euclid. And even if you think of ground-based observation, you can reach similar field of view, but the resolution is by nature degraded because of the atmospheric turbulences, and that's why we wanted to go to space, and this is unique about Euclid.
Fantastic. And Francis, you are one of the leaders of the Euclid Consortium.
Yeah.
Can you tell us a bit more about the consortium and its role in analyzing images such as this one?
So the consortium has been built, actually, and defined for the scientific exploitation of Euclid and for the full mission, for the 6-year mission we've heard about before. So it's in charge of many things, right? Many tasks before on the consortium. The first one was to design and build the 2 instruments, the VIS and NISP instruments. It's actually in charge of organizing the observations, so actually using the instruments, right? Doing the processing of the images. And Jean-Charles is one of our specialists in doing that. And then finally to do the analysis, right? the scientific analysis of the data we will get. That requires a huge variety of expertise, and actually the consortium now gathers the expertise of more than 2,500 people, scientists, engineers, technicians, facing all of these difficulties, all these tasks. One number. At the end of the mission, 6 years, we will have about 1 million images to analyze. That requires specific tools, specific knowledge in data analysis. Obviously, we will start with these images, right? And scientists have already, well, processed the images, Jean-Charles, and started to analyze them in the scientific content and a publication. Scientific publication will appear in a few months. That will be detailed what we see actually here.
Fantastic. Looking forward to this. Now, Jean-Charles, Francis has already mentioned it. You actually led the processing of the data we received from Euclid to create these stunning images. Can you tell us what that felt like, what that process was?
Oh, it was amazing. Yeah, so I had the distinct privilege of having access to this first data. And there were a special program that was made to make people dream about what we're trying to do here. And so there was like Carol said, I think 24 hours of operation of Euclid that went to these images. And so, of course, Euclid doesn't take a picture like your phone takes it. And, it requires quite a bit of work, especially it goes from the infrared to the optical. You have to shift a bit like René was explaining about, how you build this. And so, obviously, for this small program of these 5 images, there was already quite a bit of work. So I'm sure it's going to be a lot of work for the 6-year mission. And so what we have here was a complex process to take the data that come from space, which are affected in various ways, into what you're seeing today.
And I think we actually have a close-up of the star-forming region, and I was very curious about this purple color. Maybe you can tell us more why it looks that way.
It's a very good question about what is the colors of the Euclid image. What do they mean? So I'm very attached when I picked the right colors, the bands. And Euclid is very sensitive to certain colors in space. And so how do you transfer this to our human vision on a screen like this one or on your phone? And so I made a choice that really maximize color range. And so things are rich. And so that's what you see in all these images which are released today. Is like you have to have some oomph, right? You have to really vibrate and talk to the people. And so, for example, this one is a star formation region at the vicinity of this galaxy, this small galaxy we're talking about. You see a sprinkle of stars, which are like a dancer. So it means they've been formed at some point. And so the color is purple. And so why is it purple? If you take the RGB, red, blue, green, and red, it means you have blue and red together. And so the blue is actually, as René was explaining, shifted from what we would see in the optical. It's what we call ionized gas, right? It's a part of the formation process when you have hydrogen, which is excited by young stars, so it shines like in blue for Euclid. And then you have like dust scattering and so on that are adding component in the more red. So when you put the two together, there's no really light being emitted in the middle. You get purple. So there's purple in the Euclid images.
Fantastic. Love that color.
Excellent.
Francis, why are such crisp, clear images that we get now useful for scientific purposes?
Yeah, this is a word, crisp and clear, and resolution is a key word for me. Well, you can really look in the detail. I can see it here. They are in the background of these stars, of this blue region we see. Well, region we see here. We see many galaxies, and this is what we are after. Basically, what I'm saying that the resolution is good over the whole picture. It is good in all wavelengths, in all colors, and that makes things possible for me, for the consortium, to identify a very large number of these background objects, and these background objects will be used to derive what we want to derive out of Euclid, that is constraint of dark energy and reconstruction of the expansion history of the universe.
Fantastic. Thank you very much, Francis and Jean-Charles, for
You're
joining me. Now, during its mission, Euclid will generate vast amounts of data, the equivalent of about 1 million DVDs. And it's fascinating to hear how we turn all of those ones and zeros that Euclid sends down to Earth into the stunning images we are seeing today. And now we are entering inside the Milky Way galaxy, our home in space. Our next image beautifully illustrates how much information Euclid can capture in each shot. Let's take a look. So this image actually brings us 2 times closer to home yet again. And here what we see is what's called a globular cluster, a collection of hundreds of thousands of stars bound together by gravity. And this is actually the second closest globular cluster to Earth. Now, joining me today is Reiko Nakajima, a scientist working on one of Euclid's instruments, and Giuseppe Recca, Euclid project manager. Reiko, could you tell us more about what's so special about this image?
Yes, as previously mentioned, to have the entire globular cluster in one field of view is a feat that currently only Euclid could do in space. And so we have this enormous field of view that contains all the stars in the globular cluster in one field of view, but also at the same time the high resolution where we resolve the single stars and we could count how many stars there are. In fact, the resolution is good enough that we can actually see background galaxies behind these clusters of stars. It's quite amazing. And on top of that, there is a little bit of processing magic that happens. When you want the faintest stars to show up in the image, you take a longer exposure. But when you do that, the brighter stars can wash out the image, parts of the image. And in order to avoid that, what Jean-Charles did was he combined long exposure images with the short exposure images so that we could resolve both the bright and the dim stars.
Fantastic. And how exactly does the design of Euclid enable it to capture unique images like this one?
Right. Euclid was designed as a wide field imager, which means the telescope was designed so that it could capture a big portion of the sky at once. And this is an enormous engineering feat because you have to be in focus at this end of the corner, this end of the image versus the other end of the image, just as in focus as it is in the center of the image. So there's the telescope design. We also have to have lots of pixels, 600 million more, more than 600 million pixels. And so that is in the VIS instrument. On top of that, we have to have an extremely stable pointing. If the spacecraft is jittery, we're not going to get crisp images. But we now have a very stable spacecraft.
Fantastic, and so many things to consider for such an image. Giuseppe, you managed the entire Euclid project up until recently. Was this the kind of image you were expecting it to produce, or does anything surprise you?
It's actually the kind of image we were hoping to achieve, and we are really very, very satisfied and proud that we managed really to achieve and to have this quality, the image quality itself, as Raiko was saying, the jitters, the stability, the thermal control, everything really turned out to be really has the objectives were. So that's really a great satisfaction.
Fantastic. And how exactly will scientists use Euclid's images of globular clusters?
The scientists will observe this and will try to find also particular effect which is related to the general objective of Euclid, which is actually to map the dark matter across the universe, so between galaxies. And we will not be doing that generally within our own galaxy, but this type of images can also be used by the scientists to really look at the distribution of dark matter also inside our own galaxy and around this globular cluster by looking at particular effects, how the distribution of the visible matter is, how the stars are behaving, if there is certain things like tidal tails are called, and that would give an indication of what the dark matter is also inside our own galaxy. So it's really something, a bonus in comparison to what the regular observation of Euclid will be.
Oh, incredible. Thank you so much, Raiko and Giuseppe, for joining me. So, as Raiko mentioned, no other telescope in existence can capture an image like this in just one sitting. They would need to take lots of smaller images with different exposure times and combine these together in a mosaic. So it's wonderful to see how Euclid is heralding a new era of astronomical imaging. So we still have one very special image to look at, and I'm extremely excited to share that with you. But before this grand finale, I want to talk to a couple of experts on how we have reached this point. Since its launch on the 1st of July, Euclid has faced some challenges, and I know that so many people have worked together brilliantly and put in a huge amount of effort to make sure that everything is operating. I have with me Micha Schmidt, who leads the operations of Euclid at ESA, and Paolo Musi from Thales Alenia Space. Thank you. Micha, could you tell us about some of the challenges you faced with Euclid over the past few months and how you've managed to overcome them?
Yes, thank you, Chiara. So first of all, I mean, the launch and the early orbit phase and then commissioning is really the climax of the work. We are being prepared for that, so we start a couple of years before the launch to follow the development and develop our systems here. And then we go in some sort of simulation campaign here in this control room, the main control room. So this was our home. And then you come to the launch where you really feel prepared. And then everything comes differently anyway, and you have new challenges when you see the spacecraft working. But first, I would like to emphasize that actually we had a huge amount of tasks on our plate. We had 94 major blocks to be done. We wanted to do them in 45 days, but then Giuseppe, who was here before, told us, no, you do it in 31 days. And we tick marked one after the other. Yeah, and this was really smooth operations. And thank you very much, Paolo, for this nice machine. And we were able to do challenging things like the focusing or like even the decontamination. We were tilting the spacecraft to an angle which was not foreseen. So a little bit of sun was shining on forbidden areas and so on. This all worked smoothly, but then there are challenges, of course. And these three major challenges, or the elephants in the room, you may have heard already before, where first of all we discovered stray light, which should not have been. This was easy to correct. So after it was identified, actually we allow the spacecraft only to turn in a certain direction such that the sun shield actually hides the reflecting area from the sun. So this was not easy for us because we avoid this. It will be more a challenge for the people doing the survey later on because they have harder constraints. Second thing was X-ray. We cannot do anything against this will occur. So we will lose 3% of the observations. We have to redo them or you take this into account in the processing. And then there was another specific challenge. You need to keep the attitude of the spacecraft very accurate. So if you take a picture, you should not shake because otherwise the image becomes blurry.
I think we have an example of, I think they're so-called loopy stars here, where you can maybe explain.
Okay, thank you, Chiara. All the scientists get nice pictures and you give me that, thank you. Okay, so if you would like to keep stable, imagine that actually Euclid would be on top of Mount Everest and would looking down to the sea level. Once locked on a star formation with a special fine guidance sensor which was developed specifically for this mission, you would be able not to leave the area of the bullseye of a dart plate. So that is 1.2 millimeters, yeah, for 15 minutes. But even more, it's not Mount Everest, it's 3 times Mount Everest. Yeah, and of course the FGS was not doing that. So actually, yeah, so it was looping because the fine guidance sensor could not lock on the star formation because it was taking artifacts which come from cosmic rays and could not distinguish it from stars. So then the industry went back on the desk and found a solution. We have updated the software. The software was loaded on board after some testing on ground, and the problem is solved.
Fantastic. Thank you so much. And it's really interesting to hear those numbers and imagine it with Mount Everest. So thanks for that example. Now, Paolo, you work for Thales Alenia Space, the company tasked with developing Euclid. What has your role been in the commissioning phase?
Yes, the commissioning phase has been quite an intense period, as Mika was recalling. And the design team from industry, and from industry I mean Thales Alenia Space as prime contractor, but also key industrial partners like Airbus and Leonardo and other partners, provided engineering support throughout the commissioning phase. Long days, also some long nights, quite some excitement, and a lot of satisfaction at the end. I want to recall 3 special, let's say, key moments of the commissioning, which made this extraordinary images published today possible. One was the cold stabilization of the focal plane of the telescope. We need low temperature for the infrared sensor. The second key step was the fine alignment of the telescope on orbit, where you can get rid of the gravity and the air, and you can do the perfect alignment. And the third key moment was the proof of the stability of the pointing of the system. And this last step required some extra weeks, because as suggested by Mika, we characterized the performance of the fine guidance sensor in a wide range of star density, from very low density and faint star to very populated field, and find out that at the extremes, the sensor could lose track of the stars. So after analysis of the data, we decided to add a piece of software which was better coping with the spurious stars generated on the sensor by the cosmic rays. And this was loaded in September, the second half of September, and I think we are quite happy of the results after this recovery. And I would also take the occasion to thank ESA and the science team for this improvement that we were able to make, because when we have to do with the optimization of an end-to-end performance, we need all the stakeholders as part of the team, and I think we played a good teamwork.
Fantastic. Thank you so much, Micha and Paolo, for joining me. So now that teams across ESA have solved routine and not so routine problems to get Euclid working so well, the dedicated operations team is doing the final fine-tuning of the spacecraft before routine science operations begin in early 2024. Now, just before we reveal our final image, we've got a special message from our friends over at NASA.
It is so exciting to be here virtually with you today to celebrate the first images from Euclid. This observatory will uncover a treasure trove of scientific discoveries that will be used across the world, including by US scientists, for years to come. NASA is a very proud contributor to this mission. We have been responsible for key pieces of hardware and engineering support, as well as a US-based science data center at IPAC in California. Additionally, NASA has provided funding and support for the US scientists to analyze Euclid data and contribute to the mission's science goals. Euclid will make a 3D map of nearly a third of the sky, containing billions of galaxies. Together, ESA and NASA are paving the way for a new era of cosmology, providing huge amounts of detailed data about the history and the structure of the universe. NASA's forthcoming Nancy Grace Roman Space Telescope, on which ESA is a valued partner, also seeks to answer key questions about the nature of dark matter and dark energy. Roman will build upon what Euclid learns about these mysteries and will additionally survey objects on the outskirts of our solar system, discover thousands of new planets, explore nearby galaxies, and much more. So congratulations to the Euclid team. I'm excited to see the dark side of our universe through Euclid's eyes in the years to come.
Thank you so much, Nicola Fox, for that kind and inspiring message. NASA has played a vital role in the Euclid mission. For me, hearing about all of these clever fixes that the team has come up with to solve the challenges Euclid has faced makes this last image even more impressive. Now, I know that many people will recognize this famous celestial beauty from images by other telescopes, but Euclid has brought us a whole new view. Let's have a look. Never before has a telescope been able to take such a wide and sharp view of the Horsehead Nebula in just one observation. And I'd like to welcome back Carol Mundell along with Jason Rhodes from NASA. Carol, I have to ask again, why is this image so special?
Well, again, it's this huge field of view. This was just 1 hour of observations with Euclid. And as you saw, as we had the zoom out, you could actually see little distant galaxies. I saw a spiral galaxy, a barred galaxy. So there are galaxies hidden in here. But of course, this is a very local neighborhood for us. And this is a very famous stellar nursery, really. Stars are born here. You can see dust, you can see gas, and you can see lots of physics that we'll be extracting from this image. But it's the sharpness, the crystal clear crispness, the very wide field of view, and the incredible detail that we've got, along with the sensitivity to faint light across all of the bands combined together, that make this image so special. We could make this up with other images from other telescopes, but it would take us an awfully long time to take an awful lot of observations and stitch them all together. So, you know, you just get that with one hit.
Fantastic. And Jason, can you give us an insight on the kind of things that we can see here in this image?
Yes, in this beautiful image, as Carol said, we have a stellar nursery. We're seeing stars being born. And what we see here is gas and dust that comes from the explosions of stars that have ended their life in a violent explosion, spewed that gas and dust out, and that gas and dust is starting to coalesce to form new infant stars. In addition to the stars, we're seeing the formation of planets. Some of those planets will be bound to the stars, like our planets in the solar system are bound to the sun, but some will be free-floating planets, not bound to any star. We also call those rogue planets. In addition to the stars and planets, we hope to find brown dwarfs in here. Brown dwarfs are too big to be planets, but they're just a bit too small to be stars and undergo nuclear fusion and give off their own light. But what we see here, the stars, the gas, the dust, and the planets and the brown dwarfs, they're all hot, and so they're giving off heat or infrared light. And so this is an image that makes great use of Euclid's infrared camera. The detectors for the infrared camera were provided by NASA, my employer, and NASA is a really proud part of the family of people making Euclid happen. So this image as a whole is a really great image for us to showcase the use of that infrared camera. Now, if you were to walk outside tonight and look at the night sky, you wouldn't be able to see this Horsehead Nebula with your naked eye because it's too small. But if you wanted to find it, you can find it in the belt of Orion.
Fantastic. And I love the imagery of a star nursery. It sounds wonderful. But Carol, I'm so curious, why exactly do we see this horsehead shape?
Yeah, so you can see this almost fold of or plume of dust and gas. And the reason that we see it almost as a shadow, it looks like a dark shadow, is because the actual ultraviolet light that's being produced by the very young stars is absorbed by the dust. So this is a tracer of the dust. And as Jason said, in the infrared, the dust emits light because you see it in the thermal, the heat signature. But in the visible bands, the dust actually absorbs the light from the ultraviolet and the blue parts of the band. And so you get this incredible shape. And that really tells you something about what has produced this dust. And it's although it's a static picture, you can see it feels almost dynamic.
Fantastic. Now, Jason, how does studying the Horsehead Nebula help us understand dark matter and dark energy?
So while Euclid's main goal is to understand dark matter and dark energy, we're going to do that by looking at visible objects, visible light. And what we see here is stars in formation. And understanding how stars form and evolve and how those stars come together and form galaxies and how those galaxies evolve is going to be critical for understanding the underlying physics of those galaxies. And it's studying those galaxies that is going to be what we do to help understand the dark universe.
Incredible. Thank you so much, Carol, and thank you, Jason. Wow, what an amazing image to end on. I hope that most people agree that these images are absolutely beautiful. But we are just at the very beginning of Euclid's journey. Before we conclude our event for today, we must absolutely discuss the next steps. So I am now going to be joined one last time by both René Laurais and Guadalupe Cañas Herrera to discover what is next for Euclid. René, I mean, these images are visually stunning, no doubt about that. But could you tell us more about what they mean for science? Will we get any results out of them soon?
Yeah, you have heard the beautiful stories and also the kind of science and physics you can do. And there are indeed astronomers and physicists looking at these images and try to analyze and get the results out, what was mentioned before. So they are now working on papers in their analysis, and these papers will be published the beginning of next year already. So there is really a frenzy in getting this first data out.
Yeah, that's very
We
soon.
will also release all these data so that the whole world can also look at these images and do science on it. So the analysis can be done by any scientist in the world in the beginning of next year.
Fantastic. And Guadalupe, as a theoretical cosmologist, how do you feel about the science promised within these images?
Well, it's a really important milestone, definitely. What these images can actually tell us is that the instruments of Euclid are working fantastically, that we are getting ready to start with the ultimate goal of Euclid, that is create this huge survey of 1/3 of the sky, which is what we need to actually to go through the most interesting cosmological secrets of our universe. So trying to understand what is the nature of dark matter, that energy, and the underlying distribution of these ingredients all over this space. So really exciting, feeling ready, feeling motivated with these images. It couldn't be better, yeah.
Fantastic, and I really feel the excitement today as well. So thank you so much for sharing this. Thank you, René, and thank you, Guadalupe. I mean, I can only say it again. Wow, it's incredible. Today is a big day for Euclid. It is a big day for ESA, and it is a big day for humankind. To all of you watching, this is your telescope. And as these images show, Euclid is shaping up to be a truly incredible mission. I want to say a big thank you to all of our speakers today, to the staff and the crew, and thank you to all of you at home for joining us today. It has been a pleasure. A big thank you must also go to Jean-Charles Couyondre and his friend and colleague Giovanni Anselmi for the creation of the wonderful images that we've been able to look at today. I'm Chiara Monter, and I'm very happy to have hosted this event to this point here in Darmstadt. Please do visit ESA's website, which you can see on the screen, to take another look at these stunning images. Download them in high resolution, zoom in on interesting features, see videos that pan across them, and read more about the objects that we can see. Euclid is ready to start its scientific journey into the dark universe, and we've seen the beautiful views from this edge of darkness. But this is just the beginning.